Welcome to Hartman Math. Today we're going to look at complex numbers. Before we do that, a little warm up here, so go ahead and simplify the square roots here for numbers 1 and 2. Pause the video here, come back when you're done. All right, number 1, we're going to split that up with the product property. Square root 4 times square root 11, as 4 is a perfect square. And then that becomes 2. So our final answer, 2 times the square root of 11. Number 2, we'll begin with the quotient property. Break it up, square root numerator over square root denominator. And then we do know that square root of 1 is 1. And we're going to need to fix the denominator. We're going to need to rationalize that. So we're going to multiply top and bottom by the square root of 5. And we get on top the square root of 5 over 5. Today's lesson is 4.10 Complex Numbers, Part 1. And it all comes and stems from the square root of -1 is defined to be the imaginary number I. That means that the square root of -a, where a is a real number, we could break that up to be square root of -1 times the square root of a, and the square root of -1 is I. So I kind of think of the negative just coming out as I times the square root of a. So an example of that, square root of -5 is I times the square root of 5. And then if we want to look at other powers, other whole number powers of I squared. So we can just take this definition, this equation, and square both sides. So if we square this side, we get I squared. If we square the left side, if we square the square root, they just cancel out. And we get the radicand, the number underneath, we get -1. And then I to the third, we can break up and use properties of exponents, the product property that says, well, I to the third is just I squared times I to the first, because when we multiply with like bases, you just add the exponents. And I squared is -1, and we're going to say that I to the first, anything to the first power is itself. We just say that that's I. We don't go back to here. We want to have this in terms of i's. So -1 times I is I. I to the fourth power. There's a couple ways we could do this, but the easiest is I squared times I squared. Again, multiplying with like bases, we add the exponents. 4. And I squared is -1, so -1 times -1 is 1. Let's look at another one, I to the fifth. I to the fifth. And the easiest way to break that one down is I to the fourth times I to the first. I to the fourth times I to the first. I to the fourth is 1. I to the first is just I. So 1 times I is I, which is the same thing as I to the first. So the pattern starts to now repeat itself. If we did I to the sixth, you would find it's -1. I to the seventh is -I. So this is the cycle that repeats, and there's 4 different answers. So it just kind of repeats between I, -1, -I, 1, I, and it keeps repeating like that. If we went backwards a little bit and did I to the 0, then we're talking about the 0 exponent property, that any number to the 0 power is always 1. So I to the fourth is 1. I to the 0 is also 1. Use this idea to simplify I to the 50th power. What we're going to do is we're going to take advantage that it is a cycle of 4 different answers, and it repeats that way in a predictable pattern. So we're going to take our exponent of 50 and we're going to divide it by 4. We're going to do this long division, not on a calculator. We're going to see why in a second. So let's go ahead and divide 4 into 50, long division style. 4 goes into 5 once. Multiply the 1 and the 4, stack it underneath. We'll subtract those, and then bring down the 0. 4 goes into 10 twice. 2 times 4 is 8. Stack that underneath. And we get 2. Now what to do? We're not going to do the decimal, so I'm not going to put a 0 here. We don't want the decimal. That's why we didn't use a calculator. We're not going to turn that into a fraction. That's another option. We're actually going to go back to possibly the first way you learned long division to say that that's the remainder. So it's 12 remainder 2. The reason why that's relevant is because the remainder takes us to actually pretty much the answer. What it says is I to the 50th power is the same thing as I to the 2nd power. We just learned before that I to the 2nd power is -1. That's our answer. The reason why that works is, again, exponent properties. We divided by 4, so we really kind of started with I to the 4th. We've got 12, which means that's raised to the 12th power. So when we raise a power to a power, we multiply the exponents. This becomes I to the 48th. There's 2 more i's left to get to that, so it's times I squared. Well, remember, I to the 4th is just 1. 1 to any power is 1, so that part just kind of disappears. We're left with the I squared. So that's why it works. Now all we got to do, just divide by 4. The remainder essentially connects to the answer, I to that power. And then we just remember what we had learned before, that I to the 0, if the remainder is 0, I to the 0 would be an answer of 1. If the remainder is 1, we're talking about I. The remainder of 2 is -1, and the remainder of 3 is -I. All right, go ahead and try this one. Pause the video here, work it through until you have your answer. Dividing by 4, we get a remainder of 3. So I to the 35th power is the same thing as I to the 3rd power. And I to the 3rd power is -I. That's our answer. All right, the complex plane. I'm going to start with complex numbers in standard form, which is a number that is written in this A plus BI form. Real number plus real number times I. So it might be -3 plus 5i. That's in standard form. If I comes last, that's in standard form. The complex plane, remember the regular coordinate plane has an x and a y axis, but the complex plane has a real axis and an imaginary axis. We're talking about taking a number in this form, -3 plus 2i, that's standard form, and plotting it as a location in the complex plane. So this is the real part, that's on the real axis. So -3 means go left 3, and then plus 2i, positive 2 is the b part, means go up 2 in the imaginary direction, up 2. So left 3, up 2, talking about the number -3 plus 2i. Go ahead and pause here until you figure out where we would put the complex number 2 minus I. All right, we're going to go real number, right 2, -1i, so we're going to go down 1, right 2, down 1. There's our complex number 2 minus I. Next thing we're going to look at is using these imaginary numbers to solve more quadratic equations. If you remember from a previous lesson when we were talking about the discriminant, if the discriminant came out to be negative, we would get 2 imaginary solutions. So now we're going to be able to come up with those imaginary solutions. So if with example 3, I'm not seeing an x, so I'm going to go ahead and solve by the square root method, which means I'm going to isolate the x squared. So we're going to go -4 first. And I want to get rid of the half. I don't want to divide by a half because dividing by fractions is pretty tricky. So I'm going to multiply by the reciprocal. I'm going to multiply both sides by 2 over 1. which is just 2. So I'm going to multiply both sides by 2. We get x squared is equal to negative 50. Now we're going to square root both sides. Don't forget our plus or minus, square root of negative 50. First thing I want to do is use that definition from before and say the negative is going to come out as an I, because we're going to really break this up to be the square root of negative 1 times the square root of 50. And the square root of negative 1 is I, so out comes the I. Now we can break up the 50, product property, and say that's root 25 times root 2. We know that this is 5, and the last thing we're going to do is just style-wise, kind of think of this like it being a variable like an x. We wouldn't say x5, we would say 5x. So we're going to switch the order right here. It's still going to stay behind the plus minus. X equals plus or minus 5I times the square root of 2. Now technically that is not standard form because I did not come last. We were not told that it needed to be in standard form. If you need to be in standard form, you would actually switch it to be plus or minus 5 times root 2 times I. Just make sure that the I is clearly after the root and not underneath it. All right, go ahead and see if you can solve this one. Pause the video here until you got it or until you get stuck and need some help. All right, our first stop might be to factor this double bubble situation. I don't think we're with the plus 65. There's not a lot of options there, and we can't really get the negative 10, so we're going to have to go some other option. And I am liking that it's just x squared in front, and this is even, so I'm going to do completing the square, which means we're going to remove the plus 65. We're going to go subtract 65 both sides. Now we're going to complete the square. We're going to divide the b by 2, negative 5. Now square that, and you get 25. So we'll add 25 to both sides. Now we need to write the left side as a square of a binomial. Always x in front there. And we did square negative 5 to get that, so we'll put the negative 5 next to the x. All right, we're ready to square root both sides. Remember our plus or minus. The negative is going to come out as I. Add the 5 to both sides, and we like to do that in front of the plus minus. Now we just need to break down the root 40, looking for a perfect square, so it's square root 4 times square root 10. And this is 2, and again, order, style-wise, we would like that to be 2i. And no, we cannot add these together. We can't say 5 plus 2 because it's not 2. It's a 2 times an I times a root 10. So this has an I, this doesn't. So they're not like terms. This has a root 10, this doesn't. They're not like terms. So we're going to keep them separate. Those are our final solutions. There are 2 of them, 5 plus 2i root 10 and 5 minus 2i root 10. Example number 4. Solve this one. Another one that looks like we might be able to factor. Well, with 1, the only option we have is x plus 1 and x plus 1. That would make it 2x, not a 1x, so it doesn't factor. And since it has an x, I don't want to do the square root method. And since it's a 1x, with being odd there as a b value, I don't want to divide that by 2 and square and get a messy fraction. So I think quadratic formula is our best way to go. 1x squared plus 1x plus 1, so a and b and c are all 1. Let's plug that into the quadratic formula. Opposite of b, plus or minus the square root, b squared minus 4 times a times c, all over 2 times a. So if we simplify, remember our discriminant here, 1 squared minus 4 times 1 is negative 3. 2 on the bottom. And then the last thing we do is the square root of negative 3. The negative comes out right there as an I. I think that's as far as we can go. So x equals negative 1 plus or minus I square root 3 all over 2. Final answer. That's it for today. I'll see you next time.